Good morning, everyone. My name is David Saylor. I'm Vice President of Public Affairs for the university, and it's my distinct pleasure to welcome you this morning, distinguished guests, Breakthrough Prize laureates, faculty colleagues, students, friends. Welcome to the Breakthrough Prize Breakfast. Today we celebrate the pursuit of knowledge and explore the future of research in the fields of life sciences, mathematics, and fundamental physics. We begin today's presentation with two panel discussions on these topics. Later today, we will explore these ideas further in three scientific symposia that were so popular with our invitees that they will fill this room and two additional campus facilities. And to start this terrific day, I'd particularly like to thank the Breakthrough Prize sponsors, Sergey Brin and Anne Wojcicki, Mark Zuckerberg and Priscilla Chen, Jack Ma, Kathy Zhang, and Yuri and Julia Milner. Please give them a round of applause. Our first panel will present three university leaders, and I'd like to introduce them now. Stanford's 10th president, John Hennessy, Chancellor Sam Hawgood of UC-San Francisco, and Vice Chancellor for Research Graham Fleming of UC-Berkeley. I'm pleased as well to introduce Fred Guterl, the executive editor of Scientific American, for not only helping to make this morning's panel discussion possible, but also to be the moderator of our conversations this morning. Please join me in welcoming our first panel and our special guest moderator, Fred Guterl.
Thank you. Please. Hello, folks. It's a pleasure to be here, and I want to thank you all for coming. And I want to thank Breakthrough Foundation and Stanford University for making this possible. And I want to thank also all the people who are watching this beyond this room, which is being live streamed. It will have a place on the internet where people will be able to come back to it. And I think that's important today because I think we're kind of the choir here. We understand and appreciate science, and I think one of the overarching goals of this whole enterprise is to get people beyond the scientific community to appreciate what scientists do, because we live in a democracy, and so we need an informed citizenry. And we need people who appreciate that science is a human endeavor, and it's full of all the dramas and the excitement and the complexity that most human endeavors are. And with that, we have the distinct pleasure of having a conversation here with three university presidents. And these are the people who are standing between the researchers and the scientists on the one hand, and the barbarians on the other hand, who are, the politicians, the media. I include myself in the barbarians, my group. And I'm being a little silly, but these are the folks who have to make it work. They have to find some way to keep the scientific enterprise going in the midst of a world that is full of Sturm und Drang and changing, and a changing research landscape, changing funding landscape. So we're going to have a conversation along those lines right now. And I'd like to start by asking John Hennessy where the next breakthrough is going to come from. Now, I know. I'm told that he is very adept at handling broad, open-ended questions. So that's what we're going to give him.
So let me just start. There's a famous quote that Alan Kay, the person who envisioned what we now think of as laptop devices and personal digital devices, once said. He said, "It's easier to invent the future than to predict it." So with that understanding, let me just mention 3 areas that I think have tremendous opportunity. The first is in the neurosciences, where I sometimes say as an analogy, we don't yet have the double helix that explains how the human brain works. We're really in the infancy of this. I think it's a fascinating field because it's going to bring together so many different disciplines, people in engineering and the applied sciences that are going to build interesting instrumentation to probe and understand how the brain works. Obviously, the neuroscience, the traditional neuroscience community, neurobiologists, cognitive psychologists, people who work in psychology and work on issues like memory, and people in education schools who, for the first time, might actually begin to understand why somebody who has dyslexia, what's functioning differently in their brain than it functions in a normal brain. So I'm really excited about this area. I think we are just at clearly there's been a lot of work done, but the next jump is a big one. The second area that I think is extremely interesting is the whole area of new battery technologies. More applied, but building on quite basic research, whether it's quantum dot style designs or next generation lithium-based batteries, really going out over the horizon. Because if we could do, I think, if you could get a factor of 10 improvement in batteries, we could do more to change the picture of carbon loading in this country than virtually anything else. That's a big job. It's a long gap between building a battery in a laboratory and going out and building millions of them that work, that are reliable, that don't catch on fire, that can have long lifetimes. But it's an interesting area. And the third one is a kind of bit of self-interest. Everybody in this room has benefited from the enormous progress in information technology over the last 60 or 70 years. That's been driven by the fundamental discoveries of the integrated circuit, which of course in turn was based on quantum physics and the discovery of the semiconductor. We're nearing the end of this remarkable revolution we've had with silicon, and this Moore's law is already slowing down, and you can begin to see it asymptote out there. We're so used to having more computing power year after year, being able to get faster phones, faster interconnection. If we don't find an alternative technology, that's going to end. Whether it's 20 years or 30 years, we're at the beginning. So if you want to invent an alternative technology, whether it's organic semiconductors or carbon nanofibers or something else, you better start today, because it starts with people doing basic physics that are 20 years ahead of, or 30 years ahead of actually a new technology that we would actually distribute and companies would start building competitive technologies with. So I think that's a critical area. We don't yet have the breakthrough, but I think we have some signs that there might be a breakthrough there.
Oh, that's great. That's terrific. That's just the kind of stuff that we do at Scientific American all the time. I've been remiss in not pointing out that you have copies of this out in the back that you're already reading. So now we turn to Sam Hawgood. Now you're in addition to being Chancellor of UC-San Francisco, you're Dean of the Medical School. So maybe you could tell us a little bit about what you see coming down in medical sciences and what your priorities are.
Sure. And just a slight disclaimer, I was Dean of the Medical School, but I certainly come from a health background. I think to me there are two very interesting enabling trends that are emerging, and John touched on neuroscience, which I couldn't agree more is a very exciting area, although I am reminded that when I graduated from medical school almost 40 years ago now, I was told that we were about to enter the decade of the brain, and we've made definite progress, but I think neuroscience is clearly an area. But the two trends that I would like to draw out is that I think as we have increased our mechanistic understanding of disease, a fundamental paradigm that is starting to emerge that is incredibly exciting and I think will be a real accelerator over the next few years is that our understanding of disease historically has been based on the constellation of symptoms or the constellation of findings, or has been organ-based. We talk about disease of the prostate or disease of the liver. But what is emerging really quite rapidly and very excitingly is that many of these diseases previously thought to be completely unlinked and unrelated to each other are sharing common mechanisms, common pathways, common networks of proteins and signaling pathways, so that what we're learning in the neurosciences is going to become rapidly applicable to the field of cancer. And we already have some huge success stories there where, as pathways have been sorted out, a drug that has worked very successfully for one disease, let's say a certain cancer, now, because of a mechanistic understanding, can be rapidly applied in a completely unrelated disease, let's say rheumatoid arthritis, to great effect and a great reduction of the costs of that kind of translational work. The other theme that I see emerging that I'm particularly excited about, and I think in the Bay Area here we have an ecosystem where we can be leaders in this, but there are many other ecosystems around the world that are doing exactly this, and that is a blurring of the traditional boundaries across institutions and across disciplines. Boundaries that were previously relatively impervious to easy collaboration, and I'm referring now to public boundaries between great universities, such as represented up here on the stage, but also, and perhaps even more transformative, a great willingness to think about new models of how universities can interact with the for-profit world, and technology is an area where that is really going to play out, is already playing out, but I think we have huge opportunities to think of new models as to how we can work across disciplines, across business models, and across organizations to take on some of these really big problems that none of us alone are going to have the resources, the size of the data, that are going to be needed to be aggregated to use the new tools of deep learning, artificial intelligence, and other areas to advance medicine rapidly. So I'm very, very excited and optimistic that we are at one of those inflection points in the history of medicine where we see what has been fairly linear progress suddenly take off and take an exponential inflection in our progress.
Well, that's great. I'm glad to hear that we're going to have some nonlinear progress in medicine. That's terrific. Thank you. And Graham Fleming is a chemist and vice chancellor at Berkeley. What do you think is coming? Where do you think the next breakthrough is coming? What do you see? What are the big trends that you see?
So it's difficult to follow John and Sam since they've picked the ones I would have mentioned. So let me move outward quite far. I think in the last couple of years we've come to understand that we're really very far from alone in the universe, that there are an enormous number of planets in what's called the habitable zone, the Goldilocks region that's neither too hot or too cold around stars that look a lot like our sun. And what may emerge with new generation of telescopes is, rather than just simply characterizing these as little blips in the light that we see from stars when the planet passes in front of the star, we'll actually be able to characterize them in ways that might tell us whether they would be habitable for life or not. And there are billions of these planets just in our own galaxy, in the Milky Way. So this has radically changed the picture of what we think about our role in the cosmos. That, I think, is one area. I'd also like to pick up on one of the things that Sam said. We've had, over the years, a rather narrow definition of interdisciplinary collaborative research. It means chemists working with physicists or maybe chemists and biologists. And I think what we'll see is a complete breakdown of these divisional boundaries over the next few years. And all of our big problems aren't purely technical, they're social as well. And if we manage to actually meaningfully connect across the social sciences with the hard sciences, then I think some of these intractable problems may very well turn out to have realistic solutions. Finally, Sam also mentioned collaboration between our three institutions, but we exist in a rapidly changing global environment where universities in especially Asia are becoming stronger, and how universities react to that, whether they put their head in the sand and think they don't need help or an interaction on the outside, or whether we globalize in a meaningful way. And by that, I do not mean establishing campuses all over the planet. I think that will also transform our opportunities to solve problems which are universal. The kinds of energy problems that John mentioned are universal. It's everybody gets the CO2 from China. I was just in Singapore last week. We were breathing the smoke particles from Indonesia. It's a global problem. Solutions may very well be local, but we need to work collectively as a planet to solve some of these problems. So I think one of the things that characterizes my institution is a strong social mission to make the world better. And I think those are the kinds of things that we will be concentrating on in the future, in addition to neuroscience, more precise forms of medicine, and the energy area.
That's really interesting. I mean, so it sounds like everything is changing, really. Everything is up for grabs here. So the traditional boundaries between biology, chemistry, physics, and that sort of thing are becoming blurred. And the boundaries between public and private institutions are being blurred. And globally, right? There's now a global ecosystem. So this is kind of scary. I mean, all this change. I mean, what does this mean to people who are in school now? Kids who are in school now and are interested in science, and may not be getting this in their high schools or elementary schools or middle schools. What do they do? How do they get in touch with this excitement that's happening?
Well, I think it is a time when the career opportunities in science and technical fields have never been better. And most of us went into these fields for love of the field. But these are fields where there's tremendous demand for talented people as well. And I think our challenge as a country, I think our universities are great. For all the chastising that goes on in the public press about American universities, they are the best in the world. They are the best in the world. Where does everybody else come to study how to build their university? They come to institutions like ours. So what we need to do is think about the rest of our system, and I think we really have a problem in our K-12 system that we really have to make an investment in, and we're going to have to improve the teaching of science and math. So when young people arrive at college, they can pursue an interest like that because they are adequately prepared to do it. And that's something we have to be committed to, and it's going to require a major effort. We've got to put more people with science and mathematics background into schools. We've got to reward them. We've got to say, well, these people have other career choices, so we have to make it attractive for them to be in an environment where they can inspire young people.
What has to change for that to happen?
Oh, you've got to rebuild the entire K-12 system. But I think you have to rethink how schools operate. You've got to probably raise the bar on teacher salaries. You've got to break down a notion that teacher salaries should be the same across all disciplines. You've got to set higher standards. This is not going to happen overnight.
Right.
It's going to have to be a long effort. In the meantime, I think other ways of providing young people opportunities to learn and to get involved, whether it's through online courses or MOOCs or going to a summer program or a competition, robot building competitions. These are all ways to inspire young people to get engaged.
Okay.
I would just add to that. I agree. It's a fundamental societal problem, but I think our universities have a role to play. What I'm impressed and picking up on a comment Graham made, our students now are deeply excited about the global challenges. They've grown up in a completely digital age, and so they're used to connecting across continental boundaries, and they're used to thinking about big problems. So I think it's a matter of getting the enablers in front of them. The three of our institutions collaborated just 2 weeks ago on a science fair that was held at the AT&T Park. Almost 70,000 high school students in some form or fashion participated in that. So I think our role can also to be an excitement generator of what the world of possibilities is out there. Obviously, they need the teachers and the resources to follow that up, but we can generate excitement because the nascent excitement about the global challenges is absolutely out there. We find an absolute hunger for our students to get involved in these big global challenges that we described earlier.
I think our faculty and students are going to have to spend a substantially greater piece of their time trying to communicate the excitement and importance of science at all levels, and not just as occasional good works, but as a routine part of their jobs. That's something that we haven't institutionalized or rewarded in any significant way, and I think that's a change that the universities need to make, so that we weave these ideas into the education of everyone that we can.
So I think this view that universities are going to have to play a bigger role in trying to address these very large-scale problems is absolutely right. We've lost our large research labs, by and large, that were funded, whether they were at AT&T or IBM or Xerox PARC. They're gone, and I don't think they're coming back immediately. So universities are going to have to play that role. In order to play that role, I think the key is going to be that the universities have stable basis of funding, whether it's public institutions, private institutions, whether it's the federal government, the state government, philanthropy. That's going to have to be pulled together in a way that we can work on these long-term issues, because they're not short-term problems. And we're going to have to collaborate across institutions, because they're at a scale that demand that kind of collaboration if we're really going to get the breakthroughs we need.
And we're going to need to do long-term support of basic research. Absolutely. Because not all these problems can be solved with what we know right now.
Right. Well, I'm glad you bring that up, because basic research is not something that is often fully appreciated. Sam, tell us, your field is medicine, which is a very practical field. You have a very definite real-world purpose. But to what degree do you rely on basic research to do that?
It's critically important, and I love the quote that John started with from Alan Kay. And you know, the real answer to your initial question of where is the next big fundamental breakthrough going to come is the fun answer to that is we have no idea, and we truly don't. So it's critically important, even for something as you describe as practical as medicine, to commit to fundamental research, because if you look back across the history of medicine, the big breakthroughs that led to an exponential increase in knowledge arose from a completely unanticipated, unpredicted fundamental piece of work that suddenly became relevant. You know, even in recent times, Liz Blackburn's work that has led to the discovery of telomeres and you know, chromosome aging and therefore cell aging and therefore organismal aging and disruption came from a fundamental question she was asking about pond scum. I mean, she did not begin wanting to answer questions about cancer and aging.
You can imagine pond scum being ridiculed in Congress pretty easily.
You could, which is
another problem.
Another problem, exactly. So educating our decision makers in Congress, I think, is also an important role that we can at least try to make. So I think even for something as practical as medicine, a commitment to fundamental research, and not even fundamental research purely in the life sciences, fundamental research in physics, in math, in computer science, in engineering, is as likely in today's world going to generate the next big breakthrough as it is in biology or chemistry.
Can you put this in context a little bit? You know, because we're in the United States right now, but you're talking about how the research is more global, more collaborative than it's ever been. The problems are bigger. They require more resources. So so can you put basic research into that context? I mean, I don't want to talk about it in terms of competitiveness necessarily, since the world is, the world is collaborative. But why is it, is the center of gravity for basic research shifting? And what's if it's shifting, say, to Asia or to Europe? And I'm not saying it is that a problem since it's all for the United States, since it's all collaborative?
I think it is shifting to some extent, and yes, it's a problem because the workforce in Silicon Valley comes in large measure from the universities in this region, and that would be true for the next big area if it happens to be clustered around universities in Beijing or right. wherever. And so it is a problem in competitiveness. I want to just add a little bit to what Sam said. I have a motto for my office, which is facilitated bottom up. We don't ever try to tell anybody what they should do research on, but we help them, if we can, to get what they need to do what they want to do. So it is incredibly difficult to predict where the future is going. And what we have to do is just be supportive of the brightest minds and let them decide what the future is going to be.
Yeah, I think it's shifting. I think there's clear data from National Academy reports that show over a long period of time, U.S. leadership in some of these key areas kind of becoming much more global. Is that a problem? Well, I think, first of all, as Graham alluded to, there is a continuum from basic research to applied research. And having those in one country, one group of institutions certainly makes exploiting that continuum a lot easier than right. if you don't have it. I think the other thing is the young people Graham mentioned. You look at the Valley. Look how dependent we are on importing great talent from around the world. We're very dependent on it. If it becomes more attractive because those institutions somewhere else become better and are providing better opportunities, we're going to have to figure out where we're going to get the talent to continue to be in this kind of leadership position.
Okay, that's a good answer. Well, I'd like to turn it over to questions. If I'm sure you all have some, and there are some microphones floating around. Would anyone? You have really 3 big fish in a barrel here. So does anyone?
It's easy shooting.
Does anyone want to ask any questions? We have right here.
Sure. My name is Tom Hudson. I'm president of the Ontario Institute for Cancer Research. I run some big cancer genome consortium across the world, and I'm actually interested in a particular question to the speakers. It's about team-based science, particularly in medicine, where although we are more and more need to work in large consortia, this week in Boston I brought together 100 scientists to analyze one big data set, which took us a year to generate. But people still come back to us as how are we going to get promotions out of these papers, which are multi-authored. I know in physics and math there are some people have been using different ways of ushering promotions, but generally in medicine, people still look for the single investigator lab type of paper with a first and last authorship as a major criteria for promotion. So I'm kind of looking as where the universities are looking at in terms of supporting faculty development in a world of team-based science.
Okay.
Yeah, it's I think we're all grappling with that exact question, and I think we can look to physics and some of the other hard sciences for great examples where they have solved that problem. So it should not be a problem. I have to say, at least I think I can say from the perspective of UCSF. We want to test the reality versus the perception. There is a big perception out there that if I'm, part of a team that leads to a breakthrough, that's going to somehow interfere with my advancement. And at least speaking for our institution, I don't think that is true. But we need to be better at codifying that and removing even the perception that that's a possibility, because it is very clear that team-based science is going to be absolutely central to success. And some of these teams are going to look very different, as Graham alluded to. It's not even going to be a team of like individuals. And so how you're evaluated in a sociology department versus Department of Neuroscience, and getting everyone on that same plane so that we can promote bringing these disciplines together is key. I honestly don't see it as a hard problem, and shame on us if we don't remove this as a question in our institutions yesterday.
Okay, great. Go ahead.
Graham, you commented about the need to...
Sorry, can you just say who you are?
I'm Arnold Silverman. Graham, you mentioned that the social sciences and the hard sciences need to come together. If anyone needs proof, look at the $1 trillion worth of market cap that's been created in the creation of companies that are more socially oriented than technology oriented. Seems to me that there's always been a great gap between the engineering and the physics and the sciences and the social sciences and the liberal arts. How do you think universities can cover that gap, bring them together, and what's Berkeley doing about this?
In one specific area, things are falling into place. In the data analytics, data science area, our Dean of Social Sciences sitting right there, and maybe she's the one who should be answering the question. But there we've jointly, between Dean Hesse and myself, established a lab, D-Lab we call it, for the social scientists to access and analyze their data. This is the beginning of an area, and interestingly, the head of it is a professor in the law school. So that's the beginning, I think, of this trend of coming together. The psychologists work hand in hand with the molecular biologists in the neuroscience area. That's another area where we're seeing meaningful collaborations, but there's a long way to go to get this into the realm of public policy, for example. And I think we all have to think about ways of facilitating this change in the way we approach problems. We can't just write the paper with a technical solution and think we've done something anymore.
Okay, I think we have someone over here with the microphone.
Hi, my name's Whitney Ingram. I'm finishing my PhD at Berkeley in molecular and cell biology this year. And one of the questions as a future, hopefully, academic research scientist and professor is around how the university leadership is planning to interact with the policymakers of our country and potentially the world to figure out how we will be funded in the future and how to also influence policy so that these policymakers are making intelligent decisions based on what we're finding. And so any of your thoughts or ways to what the universities are planning to do?
I would just amplify what Graham said a little bit earlier. That is, I think it's all of our responsibility. Leaders in particular, we need to lead, but it's the responsibility of all of the faculty to increase both the political understanding of science. We can't expect them to be scientists, but we need to figure out a language that can speak to them in a way that they believe what we are saying around the importance of science. And I think the Breakthrough Prize and the kind of work that was put together for the award ceremony last night that made very complex science accessible and approachable. I'm not a mathematician, but I sort of felt, okay, I get that. And we've got to make science much, much more accessible to our decision makers in Congress and elsewhere, and they're going to respond to the public. So we have to have a broad base of public understanding about the critical importance of fundamental science and how that fits into our society in terms of advancing it. And this is not a new concept, obviously. It's been spoken about for years and years, but I do think we need to do a better job than we currently do.
Yeah, I think we are at a key turning point. I think for all our institutions, the federal government is probably the largest source of funding, and that they fund federal research. They fund research. this is really what led to the U.S. leadership in research and science, engineering, mathematics. It's because of that funding. It's threatened now by two things. I think one is the pressure on the budget. All that research money, as well as things like Pell Grants that support educational opportunities, is a tiny sliver in the discretionary budget left over. And there aren't very many people in Congress who view that as absolutely crucial. They've got they hear from lots of other constituents interested in other pieces of the puzzle. So we've got to get the public to stand up and realize that's the seed corn. That's the investment in the future, in our leadership and economic growth. It's vital. The other thing I think we're increasingly worried about, the U.S. stands virtually alone in using merit and peer-based review as the cornerstone on which we build our research allocation mechanism. The rest of the world, lots of politics get overlaid with that, lots of other decisions. That is why we have such a strong research mechanism, and we have to really defend this because it is critical to the success of our investment in research.
I think we have time for one quick question, and this gentleman's been waiting.
Thank you very much, gentlemen, for an inspiring talk and for the Breakthrough Prizes. So my question is in regards to building, let's say, a new collaborative model.
You identify yourself? Sorry.
Yes, I'm Matthew Frank, human biology, cancer, and immunology. So the question is, in building a new collaborative model, you'll have tensions between multi-academic places, venture philanthropy, and then moving into the private sector combined with perhaps government money that went into a particular project. And I was wondering, when you're building these new models, has there been a meeting of the mind as to what the optimal use is and sharing between these resources? Thank you very much, gentlemen.
Thank you. We need a quick answer here because we have to move on to our next step.
I think it's new territory. I think we're realizing, given what's happening on the federal front, that supporting our basic research mechanisms is going to require new models, rely more on philanthropy, more on collaboration to do big things that no one of us can do alone. So we're going to have to push out there and think about those new models to maintain this kind of leadership that we've had for so many years.
And I don't think we know the optimal model, but again, what encourages me is I think there is a great deal of interest from all of the possible players here, everyone recognizing that their little piece of the traditional model is not working as well as it should. And so there's a real openness to exploring a wide range of different models. And I think that's going to be the healthiness of this. There shouldn't be a single optimal model. We need to put together a large number of experiments and see which ones work the best.
Okay, great. Well, thank you so much. Let's give these guys a big hand.